Okay, good morning everyone. So during this lecture I will discuss the count to infinity problem, and it's also known as the two-node instability. So we are taking the example of the routers are linked up in the series. So this problem is known as the count to infinity. So that is the behavior of the distance vector routing. It exchanges the routing information with each other. So neighborhood always gets the information about the routes. It collects the information from their neighbors. So some of the time it might be considered or it might be facing some instability. So for this example we are taking the two-node instability. So let's suppose so here in this picture you can see that the networks or the routers are connected in a series. So you also know that this two value is showing the cost metric. So it means that the number of hop count or the value, how we can reach from the how much we will be for to transmit the packet from X to A or to A to B, right? So for this, so let's take the example for the first image. So before the failure, that is the initial condition where the A is maintaining their routing table. So it maintains that. So all the routes, all the routers like A and B, they wants to transmit their packet to the X router, right? So if you are at the A, so if I want to transmit my packet to the X router, I have to pay the two cost, or it's a 2 units. And the network, the next hop is dash. It means it is directly connected. While at the P, you can see the routing table here. If you want to transmit some packet to the X, I have to pay 4 cost to pass my packet or forward packet to the A, and the 2 cost it will be for the passing the packet from A to X. So it means the total cost is 6 to hand over the packet to the X router, and this can only be possible through the A, right? So in the second pin, so let's suppose, so all we know that the distance vector routing, they exchanges their information or the routing tables. Let's suppose before passing, so immediately once we gather the information from here that let's suppose the link is down between X to A, right? So immediately the A knows that the link is down, so there is no path to reach or hand over the packet to the X. So there is no path. So it means to reaching to the X, we have to pay the infinity cost or the unit. So it means there is no path, right? And still the next hop is dash because it was directly connected. Now let's suppose before handing over or before exchanging the routing table from A to B, now these hand over their routing table to the X, and which having the details about the X. So it means, so A will predict that, so B knows B having a one route to transmit their packet to the X, right? So they get the information. Now once the B hand over the routing table is exchanging the table to the A, so A determines that B knows a route other than this particular route, like X to A, right? So in that case, so A will update their table. Now A can transmit their packet with the help of B. So that's why we updated the next hop is B, and the cost is handling the packet to A to B, that is 4, and B is also knowing that there is a route to access the X to transmit the packet to the X with the cost 6. So total cost is now 10. So this problem will be going towards the infinity. Now let's second phase. So when A updated their table, so after some periodic time they will exchange their information. So now whenever they update their table, so this the B will see that, so A is updated, might be there is a change in the X to A, that's why the cost is now 10. So B will update their table because A to X is 10 and the cost from B to A is 4. So that's why there is a new route and the cost they have to pay is 14, and through only the A. So this will be in a loop, and goes up to the infinity. That is a very big problem in the distance vector routing. So to overcome this problem, there is a solution that is called the defining the infinity. How long we consider the infinity? So for the distance vector routing, the value is 16. So whenever the any cost metric will goes or be reaching to the 16, it will be considered as an infinity. It's mean there is no more route. So it's mean this routing table, like the RIP, which that's inside or the categorized under the distance vector routing, can be used only a very small network where the routes are only goes up to the 15 numbers of hops. It's mean only the 15 or 16 routers can be possible in a simple clusters, right? So another solution for this problem to solve is a split origin. Split origin, that's the problem is, if B knows that I'm getting the information about any other route, any other router, and this route is goes only from the A, so I will not share my table. So this is called the split origin. But some of the time it might create a problem, like so they might create some problem, like the information has come from A and taking information from node A, so modifying it and sending it back to the node A is what creates the confusion. The reason is, if I'm getting the information from you and also sending the same information to you, so it will create a problem. So the solution is a split origin. And during this split origin, if I'm getting something from you, I will hide this information. So I will share only the specific part. So in this example, if the B router getting the information about X from A, that actually the route is also only possible from through the A. So this particular part will be eliminated from the routing table during only the exchanging of the information, right? So, but at some of the time it may create a problem. Like in this case, the node A keeps the value of the infinity as the distance to X. Later, when node A sends its routing table to B, node B also corrects its routing table, and the system becomes stable after the first update. So this solution, the split origin, can minimize the problem or can overcome this instability of the problem. But it's not this exact solution or 100% true solution. So there is another problem that is called the Poisson reverse. In that case, if a router doesn't sends the information about any particular route for a long, the router A can see that this is the dead route. So this problem is the Poisson reverse. Using the split origin strategy has one drawback, that is normally the distance vector protocol uses a timer. So it normally uses a timer. So if a particular route is not in the use after a long, it considered it as a dead route. So if there is no news about the route, the node deletes the route from its table. So they can delete the route from the table, and when node B in the previous scenario eliminates the route to the X from its advertisement to A, so node A cannot guess that this is the due to the split origin strategy or because B has not received any news about the X's recently. That is a big problem with or the challenge for the distance vector. So the split origin strategy can be combined with the Poisson reverse strategy. So this is another solution. The solution is to not eliminate any particular entry from the routing table. If you know that this information is getting from the same neighbor to where you are sending the updated routing table, that's consider, or instead of using the actual value, use it as an infinity. So right, so node P can still advertise the value for the X to the A because it's sending its exchanging the updated table. So no need to eliminate the last row or the information about the X, but its source of the information is A. It can replace the distance with the infinity as warning. So here in this case, so whenever we exchange their info table with the A, so this value, the 6th value, will be considered as an infinity because I am getting the information from you. So I will not advise you, I will not instruct you to use my value. So this is a problem. So with the help of this, the split origin and the Poisson reverse can make the network stable up to only for the two nodes. Let's suppose, so let's consider another problem that is called three node instability. So one node instability is two node instability can be further put into in the stability, but it might create some problem when we consider the three node instability. The three node instability, so the two node stability as previous example can be avoided using the split origin combined with the Poisson reverse. However, if the instabilities between the three nodes, stability cannot be guaranteed. Why? The reason is, suppose after finding that X is not reachable from the A nodes, and A sends a packet to the B and B sends to inform them to the situation. So node B immediately updates its table, but the packet to C is lost in the network and never reaches to the C. So let's suppose this link is down and now A is updating their table. Before gets the updation from the B and the C network. So right, obviously according to the last solution, so if this situation arises, it might be put it into the stability, right? So but let's suppose when it sends the packet, when A sends their information to the C, the packet is lost, right? So the packet C2 is lost in the network and never reaches to the C. So node C remains in the dark and still thinks that there is a route to the X via the A with a distance of 2. The reason is, initially I was dependent, so initially I have a route to reach to the X via A, and the cost is 5. So whenever after some periodic time, when the C transmit their table to exchange their tables with the A and the B, so B will detect that there is another route to reach to the X, but now it is via C. So it will update their table X8C. So X is the destination network. This is cost, because the cost between B to C is 3, and already there is a cost, or the route might be a possibility, or it will be in a dark, like to reach to the X there is X5A. So now the total is 8 cost and it is reaching through the C network. So after now, because as we already know that uh, there is a solution for the two node stability is the split origin. So in the split origin, we never transmit the information, or we eliminate the particular row from where we are getting the same information to avoid the confusion, right? But now the information is getting from the C, so it is a new route. So whenever I share this information, or the B node share this information with the A, so A will detect that it is a new route, and this now it can be reached through the B. So it will update their table. Now X will update their table and hand over this table to the C. So might be all the three nodes will be goes into the instability. That is the problem with the three node instability. This problem cannot be guaranteed, and sometimes the network will be goes into the. So the conclusion or the benefits or the outcome of this video or this lecture is the distance vector routing having some infinity value, and this value is the 16, which means maximum 15 hops can be calculated or considered in the distance vector routing, right? So thank you everyone.